So this set of slides is about planets around other stars. We happen to have a picture here. So, what I wanted to show on the left picture is that what we have is just, a nearby star against the background of faraway stars. But what's going on here that we can't see is that there are planets going around. We actually have some pictures of a planet going around the star, which is kind of amazing. This is kind of a thing that is hard to know, hard to figure out. It takes a lot of work. Now, of all the topics in your textbook, this one might be the most out of date. Now, other ones are more introductory, but this one is it's going to be talking about satellite missions in the future that have already happened and ended and didn't go the way they thought they would. But we have lots of information. This is going to be mostly an introduction to how do we know that there's stuff around other stars. And when we look at stars, it's kind of obvious why there's difficulty in seeing planets around other stars. And the obvious reason is that the stars are super, super, super bright compared to any reflected light. Planets don't give off their own light. It's not perfectly true, as we talked about Jupiter and Saturn and Neptune giving off more energy than they take in. But if you calculate based on the temperature, the intensity of that light is minuscule. It just happens to be more than the minuscule amount of light they get from the sun. Right? So planets mostly reflect light. And so we're trying to see around we're trying to see exoplanets around stars. We're trying to see reflected light that is 1 billion times weaker than the actual light from the star. It's also compounded a bit. It's easier to see planets that are closer to the star for reasons that we'll go into later in the notes. And that means that it's even more hard to resolve between the star and its planet. Right, the analogy we have here is imagine trying to see a pinhead 15 meters from a grapefruit in Washington while you're standing in San Francisco. We've been able to do it in the case of stars and planets. Also, the fact that we can't do it on Earth should tell you that the Earth is round, by the way. So, this is another thing, is that for a long period of time, stars were their own thing. The sun was something special because it had planets around it, and we were orbiting around it. But stars were like the sun. But the ancient observers thought they were, like paintings on a sphere, or they were objects different from the sun. And it took a lot of reasoning and research and trying to understand what's going on to figure out that stars are what the sun would look like if they were far away. And that makes sense because they were also looking for parallax that wasn't there. So how do we ever even know that there could be a planet somewhere around a star? Now, what kinds of observations could we do that get us to seeing planets orbiting stars? So one of the obvious things you can try to do is just try to take a picture. And I'm showing you a picture where it does work. And there's a few others. As people are doing their homework, they're going to find that there's a number of different possible uh, exoplanets around stars. But that's not exactly an easy thing to do. It's still the problem of something that's a billion times dimmer than the actual star being resolved. That's often very close to the star as well. So it takes a little, you know, it's not quite what, it's not quite going to work all the time. A few special cases so far, and it'll get better as technology improves. Mostly, we have to observe the properties of the stars, of their motion and their brightness, and realize that those properties change because of something orbiting. And so we give some different methods here, and I'm sure that in your research on the topic, you'll find other possible uh, techniques. But the gist of it is you can try to take a picture directly, that's direct detection. You can measure the position of the of the star and notice that it wobbles and see that it has to be pulled around by a planet. That's the astrometric method. You can measure the spectrum coming from the star and realize that it gets alternately red shifted and blue shifted. That's the Doppler method. Or you can measure the intensity of the light. And the intensity dipping over time is because the planet goes in front of the star, or sometimes behind the star. Sometimes you're not seeing the reflected light. Sometimes you're seeing light blocked by the planet. It's a transit method. And so, these methods, if you remember using telescopes, the things you could do with telescopes, you could take a picture. That would be our astrometric method. You could look at the spectra. That would be our Doppler method. Or you can look at the timing at variations over time. That's our transit method. And so that's basically the group of things you can do. There's other techniques that are similar to these, but we're going to focus on these because mostly what we do nowadays is look at the transit method. It's easier to see planets crossing in front of bright stars. But there are a few others. So to explain what's going on, in the astrometric method, you have a star and its planet orbit a common center of mass. It's not that the star orbits the sun. No, Jupiter doesn't orbit the sun. Neither does the sun orbit Jupiter. They both orbit a common center of mass. And for almost all planets, that center of mass is somewhere in the sun. It's just not at the center. And so all stars should wobble a little bit if something is orbiting them. Now we can see that when pairs of stars orbit. That makes sense. But for some wobbles, we can't find a star, and we have to figure out that there's a planet there. Now, to look at this and see several stars, we kind of have to trace its to see several planets. We have to trace the motion of the star over time, and so here is a potential outcome. This is the path of the sun through the solar system, and what we see is a lot of different wobbles. It's not a unique wobble like this picture. So what that tells us is there's multiple things perturbing the sun's path through the sky. That means there must be multiple planets, and each one of them has some effect. And so if you can measure the motion precisely enough, you can deduce all the masses and all the orbits. Same way we deduce the orbits of the planets around the sun. So that's a hard thing to do, is that most of these things are on the order of 1,000th of an arcsecond, and that's a measurement level that's limited at this time. Right. So there is also another issue, is if this picture that we have here is kind of face on to us. We're looking at both the sun and Jupiter at the same time, and we can always see Jupiter. So we can always see the wobble. So if the planet is orbiting edge on, all right, if we can only see Jupiter when it's in front of the sun, we can't see the wobble. So there's a limitation. We can't see the star, we can't see the star's motion unless it's moving perpendicular to the direction we're looking. So the Doppler technique lets us try to find the ones we can't see with the astrometric technique. And what it does is it looks at the wobble that's built into the star based on the planet orbiting. That wobble is going to cause redshift for half an orbit and blue shift for the other half. And so we can see that alternation over time. And this is pretty accurate in the sense that we could, if we use this technique to measure a person walking around, you could see the redshift of light off of reflected light off a person walking a meter per second in a circle. It's not an unreasonable thing. Of course, the larger the redshift or blue shift, the higher the speed, the easier it is to see. And that means that there's going to be a trend. Large planets that cause big wobbles are going to be easier to see. So the very first extrasolar planet was looked at through this Doppler technique. Is that we saw a star that had a 4-day period in its red and blue shift. And we realized that had to be something orbiting with a period of about 4 days. That means it has to be really close to the star. We found a planet. It's orbiting something like the sun, but it is really, really, really close. Now, the other thing you can see is the magnitude of that. So the amplitude of the oscillation tells you something about the mass of the planet that's pulling the star around. And this is going to be basically a very big planet, a Jupiter-like planet, which is going to be a problem. Right, so the main way we find planets around stars now is to look for basically eclipses. Look for the planet crossing in front of the star and in behind the star. And so when it's in front, we're blocking a little bit of the light, and so there's a decrease in the brightness. When it goes behind, there's no reflected light because it hits the star, and there's a much tinier decrease. But the gist of it is these transits, when the planet crosses in front or when the sun crosses in front of the planet, they reduce this brightness, and it's a periodic thing. It happens because the orbit occurs over and over again. So this helps you to see the planets that are edge on to us, is that if we're looking with the planet and the star in line with us, and the planet's orbiting, moving across our field of vision, then we can see it well. All right, so basically you kind of have two sorts of measurements. Astrometric lets you see one orientation, and Doppler and transit let you see another orientation. Right, so Kepler is not an ongoing mission. It was launched in 2008. The idea was to use the transiting method to try to find as many planets as possible and to find Earth-like planets where they have Earth masses around a sun-like star at possibly the right, at an Earth-like distance. So Kepler had some problems. It lost some gyroscopes, and so it couldn't aim exactly where it wanted to, so it did some alternate missions. But the gist of it is that it worked reasonably well, is that we went and basically doubled or tripled the number of planets we've seen. So, the original mission was to look at a set of stars in a region in the northern sky. Cygnus here is the Swan, which is in the northern sky. It has some other stuff. So if you're looking toward the poles, toward the Big and Little Dipper. You'll see some of this other stuff around, and generally that's where we're trying to look. You can see there's the Milky Way and a few of the other northern stars, circumpolar stars, or nearly circumpolar. And so we were just going to point it there and look for a long time, but then the gyroscopes failed. And so when the gyroscopes failed, we kind of picked a larger range of patches where the satellite was going to point anyway. So that gave us a wider array of stars to look at. And so this is what we found. Here, so the very, very dark blue are planets found before Kepler, and the vast majority of them are going to be, I think all of them, as far as I can tell in this picture, all of them are going to be Jupiter-sized to Neptune-sized. Very big planets. And the scale here runs from a day up to about 3 years. So, this is looking at inside of Jupiter's orbit for a sun-like star. So, other methods have found a lot of planets also in that group from Jupiter to Neptune. Kepler has managed to find some that go between Neptune and Earth. So, super Earths, in a sense, between 1 and 4 Earth radiuses. And it's basically found something like 5/7 of, so about 2/3 of all the discovered exoplanets. It's been pretty productive. So, like I said, there's a few other ways of deducing that there's a planet. One is using light from a faraway star. Mass will bend light. We'll talk about that in second semester when we talk about relativity. But light can bend around a star and it can bend around a planet. And so you'll get effects in that bending, what's called gravitational lensing. And then we can see newly forming planets along with newly forming stars as features in the disks of that form around the stars. So there's some different techniques, but the three main ones, astrometric, Doppler, transit. So when we try to measure properties of the planets, we come up on some interesting stuff. So this chart has a number of planets that we found. In green are the original 8 from the solar system. And they're pointed out here, they're labeled. But the gist of this is there's lots more range in the shape of orbits, in the size of planets, in the orbital distances. The gist of this is there are a lot of Jupiter-sized objects orbiting inside of Jupiter's orbit, inside of 5 astronomical units. Right, more, Jupiter-sized objects orbiting in Mercury-sized orbits. And they're also eccentric. Some of these are strongly eccentric orbits. So things you can measure through through the techniques that let you find the planets. You can measure orbital period. You can measure the distance of the planet from the star, and you can measure the shape of the orbit. You can measure the eccentricity. Now, there's some tricks to that, obviously, but generally you can do the period from transit or Doppler, or even astrometric. You can measure how the position repeats over time. And then from the period, you can figure out the distance to the star using Kepler's third law if you know the mass of the star. And you can figure out the shape of the orbit from your observations sometimes. You can deduce the planet mass if you know the star mass. You can deduce the size, often from the transit method, seeing the planet block out, how much light does it block out. And from mass and size, you can get density. And on occasion, light going from the star passing through a planet's atmosphere will give you information in the spectra about its atmosphere properties. So, here's a summary of all the different ways we can find different information. So, Doppler shift tells us a lot about shapes of orbits. If the oscillation is skewed, if it's sinusoidal, then it's a nice circular orbit. If it's skewed, it's an eccentric orbit. And the amount of skew tells you about the amount of eccentricity. The period is going to tell you about the period of the orbit, and so the distance of the orbit, and the size of the oscillation, the velocity of the star that we measure, is going to tell you about the mass. But it's not going to be an exact thing because we need to know the orientation of the orbit. The Doppler shift can occur at an angle. It doesn't have to be straight on to us. So it gives us sort of a minimum mass. That's okay. We can deal with that. Transit data lets us figure out periods. Here is from one system, Kepler 11 is a number of transits, and from those transits we can mark out the different. Each planet has its own period, so we can mark out which dips are due to which planets. And then from the size of those dips, we can figure out the sizes of the planets, and these are things ranging between 2 and 4.5 Earth radiuses. And so from the size, if we have two techniques, one that gives us the mass and another that gives us the size, we can figure out the density. And so here, data from one source gives us a mass, say 4.5 Earth masses, but the transit method gives us a size of 1.4 Earth radiuses. That gives us a mass and a volume, and the density from that tells us that it's probably something more Mercury-like than it is Earth-like. It is a heavy metal cannonball compared to the Earth. So the spectrum changes. All right, we can kind of come out with a spectrum while we're doing the transit measurements. Those spectra can tell us stuff about the atmosphere. They block additional light at certain wavelengths and pass light at other wavelengths. And we can also kind of get an idea of surface temperature. We can look at the light in infrared, and it tells us as it varies, it tells us something about the surface temperature of the planet, which we can probably reasonably deduce from the brightness of the star and the distance to the star. But we can come up with an alternate measurement that confirms it, and generally what we find is what we think we're finding. And so the combination of things that we see here is quite interesting. Most of the planets that we can see in general are orbits smaller than Jupiter and masses larger than Jupiter. These are what we call hot Jupiters. There's difficulty in these techniques for finding planets with less mass, which usually means less size, or with larger radiuses, with larger orbital radiuses. And so we also see that the orbits are stretched out. There's a lot more with elliptical orbits. And so it's easier to find heavier planets closer to the stars because they put a bigger effect on the star, on the light from the star. So typically we found a lot of hot Jupiters, things bigger than Jupiter but closer than Mercury to the star. So here's here is a layout of possible populations. The early ones are the hot Jupiters. Some of the post-Kepler techniques that aren't Kepler will find you colder gas giants, things like Jupiter. Um, and then Kepler techniques find you things like ice giants like Neptune, or ocean like things that are very big planets. And then there's the rocky Earth-like planets, and even worse, the sort of molten bodies, the lava worlds, things that are very, very, very hot because they're close to the star, and they're probably made out of rock because they're very, very light. They're very small. They haven't held on to hydrogen or helium. So there's a range that we haven't looked at, and that is things with very large orbits, periods on the order of 3 years or so, that are also the size of the Earth. So things like Mars or the asteroids, those are kind of harder things to see. Now, those are probably going to remain harder for a while, but we have a lot of interesting stuff in these other categories. So the gist, we kind of think we've got a model of our solar system. Planets orbit in orderly, nearly circular orbits, and the inner planets are small and rocky. The outer planets are gaseous, large, and cooler because they're further away from the sun. That's not what we're finding in exoplanets. Exoplanets can have wide arrays of orbits that can be highly elliptical. They can be very big, and they can have high densities and be big. They can be what we expected Mars to look like, is something larger than the Earth and rocky. But they can also be hot Jupiters. They can be gaseous planets very close to the stars. And we kind of knew that there was a problem because I gave you a bunch of information about ways of fixing the nebular hypothesis, the grand tack, and the talking about the small Mars problem. Is we've talked about just our model. This is why we needed to adjust it. So the nebular theory thinks that big Jupiter-like planets should be outside the frost line. But we're pretty certain that that's not so, because we see Jupiter-like planets well inside a star's frost line. So there has to be some mechanism. If they're made outside the frost line, there has to be some mechanism to move them inwards. That's called the planetary migration. The idea is that the motion of the planet can cause, it leaks angular momentum. It speeds up the gas in the disk, and it pulls the planet inwards towards the star. Right? So effectively matter can, in the disk can pull the planet around. So, there's some ideas, and a lot of this is born out of modeling. You have to kind of set up a model solar system in a computer and see what's going on with it. So there's also gravitational encounters. You can have one planet flung off and another planet's in a high elliptical orbit, or lots of small pushes from other small planetesimals. So, and maybe, there's multiple planets and resonances form, the structure of the orbits. So there's ways that planets can move around from their initial orbit at formation, or their initial orbits while they're forming. And so that kind of makes us think that maybe we are only explaining our solar system, and we're not explaining the formation of planets everywhere. And so, we need, the more we observe exoplanets, the more information we'll have to explain possible things like migration or gravitational encounters. And that's basically it. That's exoplanets. The big summary here: 3 techniques: astrometric, Doppler transit, and direct imaging. Those are the 4 big things you can do. You get orbital periods, you get orbital distances, the shapes of the orbits. You can get masses, densities, you can get sizes, and maybe you can get the atmosphere properties if you're lucky, even if there's an atmosphere. And what we see is lots of planets are Jupiter-sized in Mercury-like orbits. We're seeing more that are Earth-sized and in reasonable orbits around a star. But they're easier to detect, and they seem to naturally be more common too. Is that there's methods that push Jupiter planets around that we can uh, modify our own models to accommodate. That is the last bit of the semester. Isn't this fun? So that's the last video for astronomy. I want to make some physics videos, but next week you're basically going to prepare for the assessment and finish any work you haven't done. So y'all have some good, happy holidays. It's going to be Thanksgiving and Christmas and uh, whatever else. I'm probably just going to hide in my house until January. So y'all have fun.